All right, we're going to see if we can very briefly try to go over the visual systems, how we process sight, and how that looks as it goes through the eye and rebounds around through the brain, and how our brain kind of processes that. So, how does the eye work is kind of where we need to start. Basically, when there is light that goes into your eye, that is visual sensation. Okay, that is the sense. It's like if you touch something, that's the sensation of touch. If aromas go in your nose, that's the sensation of smell. But for visual sensation, when the eye receives light from some outside source, that's visual sensation. And generally, that's light that is reflecting off other items. There are very few items that actually create light. Light bulbs, the sun, stars, things like that. But most everything is just a reflection of that light, and how your eye processes that is visual sensation. So there's this kind of weird kind of dualism in objects. They exist in two ways. First is something that you see is called a distal stimulus. So the object that you see, like if there is a shoe on the ground, that shoe is a distal stimulus. The image of that object as it is displayed on your retina, that's what's called the proximal stimulus. And so there's kind of this moment where this item exists, but it only exists so much as we see it on our retina. And that proximal stimulus is actually inverted, so I'm sure you've heard of this before. What you see, you actually see upside down, and then your brain processes it and flips it right side up. So how does that all happen? How does the eye process information? It's kind of this step-by-step process that we should make ourselves familiar with, so we can get a sense of if something goes haywire, why does it go haywire? Why do things go wrong? So first, light hits your eye and passes through the cornea, the outside edge of your eye. And that's the first point where light makes contact with your eye. And directly under the cornea is a thing called a lens. And the lens bends to accommodate for distance, for what you were trying to look at. So if you were trying to look at something closer or further away, the curvature of that lens, how much it's curved, will shift depending on where your eye needs to focus. And so that's where the light goes through next. And then at the back of your eye is what is known as the retina, all along the back, and that is basically the projector screen where this proximal stimulus is sent, and the retina is where that light, that information is received, and it is projected back on the back of your eye. And the retina is covered with two different items that you need to know and know the difference between. There are rods and there are cones. Rods are sensitive in low light. Okay, so they are what is useful to us when we try to see in a situation where there is not much light. They are located near the periphery of our retina. Those also help not just in low light situations, but with our peripheral visions. They're near the outside of the retina, away from the center point. And then cones are sensitive to bright lights. They serve the opposite function. They're located near the center of the retina. And that center of the retina area is called the fovea, and at that point, that's where there's basically only cones, and that's where we process bright lights and color vision in that area. And there's this thought that some low-level basic processing of sights, of this visual stimulus to turn it into something that we can perceive, occurs within the retina. Most of it happens in the brain, but some of that lower-level processing may actually occur right inside the eyeball, right there in the retina. And once it's hit the retina, that information passes along from the retina into the optic nerve. And the optic nerve is interesting because where that meets the brain, or where that meets where the optic nerve meets the retina, a blind spot is created. So in each eye you have a blind spot, an area where you just can't pick things up because that sight is blocked by your optical nerve. And it's different for both eyes, so you don't have like a singular blind spot, but like in your left eye you'll have one, and in your right eye you'll have one. Okay, and so this information goes to the optic nerves, and the information shoots down the optic nerves. Those optic nerves cross at what's called the optic chiasm, and half the visual information, half the information that's processed goes to visual fields in the opposite side of the brain. So there's a visual processing center in your brain, and that visual processing center receives information from both the left and the right eye. The optic nerve there's kind of, think of it as two concurrent ones. They wrap both around the right side of your retina. Those two go together, and then there's two that wrap around the left side of your retina, and those two go together. And so the ones that wrap around the left side of your retina go to the right side of the brain, and the ones that wrap around the right side go to the left side of the brain. Kind of confusing, but the textbook does a pretty good job of showing this, kind of a nice little layout of it. And so this information goes back across the optic chiasm and ends up in the primary visual cortex. That is the back of your brain, the occipital lobe. And that is where the processing begins. And it does what's called parallel processing, which means your brain is processing colors, forms, movements, and locations, and all those other things all at once. It's not like one at a time. It doesn't say, okay, first what's color, then is it moving, then what shape is it? No. All of that information is processed at the same time, so you get this complete picture all at once, essentially. And then there's this really interesting parts of the brain called feature detection neurons, that are responsible for, and the best way to describe this is seeing or recognizing different parts of patterns. So whether there's like angles, or whether there's vertical or horizontal or depth or things like that. And so this process starts at the very back of the occipital lobe, and then as it goes forward from the occipital lobe, it becomes more complex, again, as the rest of the brain does. Starts at the back, the most basic, and as it moves forward, it becomes more complex. But as it's doing so, various detector neurons are responsible for various things: the ability to see faces, the ability to recognize faces, the ability to recognize shapes as being a flower or a house or a car, things like that. And so as all of this happening is processed, it's sent to two different pathways for your brain to continue to register. And the dorsal stream tells us it's best described as a aware pathway. So it's basically, how can I be spatially aware? How far away is something? This is depth perception, right? How far away is something? How close is something? Is it to my left? Is it to my right? Like, where is this information? And that's from the dorsal stream. And then there's what's known as the ventral stream. And that is the what pathway. That is what allows a person to recognize an object. And if there's damage to either of those, then you either can't tell how close something is or how far away it is, or you can't tell what something is. You know it's close by, but you can't name it. So this is a result of these kind of feature detection neurons and then potential damage to this primary visual cortex. So that's a process, right? This light comes in through your eye, it goes into the optic nerve, it crosses over, the optic nerve on both eyes, by the way, and then it crosses over to one side of the brain where it's processed in the back the primary visual cortex in the occipital lobe, and that helps us put together what am I seeing and where am I seeing it, and then we can respond to that stimulus. And all of this is happening essentially immediately in milliseconds. So that is the process by which we see. And then one of the other things that we need to talk about is this idea of seeing in color, which is kind of a bizarre thing, because once you start thinking about things like color and shapes and depth, it starts to get a little bit weird in your own head. But essentially there's two theories. The first is what's called the trichromatic theory. And the trichromatic theory argues that the different cones in the retinas are activated by different light waves. So you have some cones that are activated with blue light waves, some that are activated by red, and some by green. And those colors are represented by different lengths of waves. And so depending on how many of those are activated, we see colors. So if we're seeing a lot of blue and red, then we're making purple. If we see a lot of those certain other colors, that's how you mix and match them through. The other theory is opponent process theory, And that idea says that within the thalamus, there are different cells that respond to different, what they call opponent pairs. And that is black and white, red and green, and blue or yellow. And this is where, well, we'll get to that in a second. But basically, if one color set is activated, then others are turned off, resting. So it's this idea where if you've ever stared at a red dot on a page, on a piece of paper, you may have done this experiment before. You stare at a red dot on a piece of paper, you stare at it for long enough, you stare at it for long enough, and you're using those red cells in the thalamus. And then when you quickly look away at a blank piece of paper, you see a green dot. And that idea is that the green cells have been resting. And so they're more then able to fire. And so that's how you're seeing these things. And this is what we call an after image. It's kind of an interesting trick. And again, both of these are theories. We're still not sure how it all works together. And they're not necessarily mutually exclusive. There's a sense that these two ideas could work together, these two theories. And the other thing that's interesting that's worth talking about is this concept of colorblindness. It's most common in males, significantly more common in males than females. So there's the thought that perhaps this is a sex-linked genetic condition. It's almost always you're colorblind from birth. So again, there's more evidence from that. And then there's two different types of colorblind people. There are what are called the dichromats, and these are people who can't distinguish between either the red-green or blue-yellow continuum, so they don't pick up on those differences. And so you'll hear people often called red-green colorblind or blue-yellow colorblind. Red-green is the more common of that colorblindness. And then the other one, which is total colorblindness, are what we call monochromats, and they only see in shades of black and white. And this is a super rare condition. Most people are just red-green or blue-yellow colorblind, not monochromatic. So that's what we've got going on. That's kind of a real brief touch-and-go overview of the visual system. It's very a complex system, but that's a way that hopefully we can start to see how it all starts to work.